A moment of wonder. When we look at modern AI writing poetry or recognizing our faces, it's easy to imagine a spark of consciousness, to feel as though a digital mind is waking up inside the machine. That mind is a complete illusion. There is no brain here, no feelings, and zero comprehension. Underneath the surface, the machine is simply executing a staggering, relentless amount of math. For decades, computers operated on rigid, manual instructions. Human programmers had to type out every single if-then rule for a computer to follow. If X happens, then do Y. It was precise, but it was brittle. Machine learning moved away from that rigid instruction set. Instead of providing the computer with human-written rules, engineers began feeding it massive piles of raw data, forcing the machine to figure out the rules for itself. This transition from providing rules to providing data changed computers from simple rule followers into autonomous pattern finders. To build a system capable of finding those patterns without human help, computer scientists looked to the architecture of the human brain. They developed the artificial neural network, a software structure made of interconnected layers of digital nodes, inspired by the way biological neurons process information. This biological blueprint serves as the foundation for a purely mathematical machine to eventually handle unstructured, complex data, like images and human speech. A neural network has three phases: an input layer receiving raw data, hidden layers for processing, and an output layer delivering a guess. Each dot is a processing node. Thousands of geometric lines violently connect every node to the next, creating a dense web. On its own, this web is static and useless. To turn data into a decision, the network must control the signal moving through these lines. Control comes from a weight, a numerical multiplier acting like a volume knob. It determines how strongly one node influences the next, powering the forward pass. High weights amplify the signal into a blindingly bright beam. Low weights turn it to a whisper. The machine's ability to distinguish a cat from a dog relies entirely on millions of these individual volume knobs being tuned to the exact correct values. When a network is untrained, those weights are set to random numbers. Show it a cat, and it processes the forward pass, almost certainly guessing incorrectly, randomly landing on dog. Told its answer is wrong, the computer creates a critical error signal, turning the output node crimson red. This triggers backpropagation. The error signal fires in reverse, sending a jagged wave rippling backward, physically twisting and retuning the mathematical multipliers along the path. The machine repeats this forward guessing and backward correcting cycle millions of times over until the mathematical error reaches zero. Artificial learning is a relentless mechanical optimization of past mathematical mistakes. Once the network has perfected its weights, it can recognize the data it was trained on instantly and with flawless accuracy. But the scale of modern neural networks is dizzying. They contain not thousands, but billions of volume knobs, interacting simultaneously in the dark. This scale is what creates the black box. Because the math is so vast and so deeply layered, it has moved beyond the reach of human comprehension. Even the engineers who built the system cannot fully trace the specific path the math takes to arrive at a final answer. We know the exact mechanical reality of how the machine learns, but we can no longer see exactly what it is thinking.